I first of all want to start out by thanking Owen for the invitation. It is an honor, actually. One of the big problems we have in academia is we don't speak enough to industry. This is actually very bad because we have an awful lot of knowledge, sometimes quite useless knowledge, but still an awful lot of knowledge. You have an awful lot of needs. We would say sometimes quite useless needs, but you have a lot of needs. Because we don't often speak to each other, we miss often important overlaps between the world of the academia and the world of industry, and both can get richer for it. So, with that short introduction, and before I continue, I am well known when I give lectures at being extremely bad at thanking people because I always forget. In the audience today we have Professor Yuri Feldman and Dr. Anna Greenbaum. An awful lot of what you are going to see today comes from them, comes from their lab where I grew up. That's why I became a scientist. So I'm starting out from the very beginning thanking them both and the students Cindy and Larissa who have supplied me with some of the data that we have here. So let's start. GHz Characterization of Materials. Why bother? Well, why bother indeed? It's a very facetious question, almost arrogant. However, the answer really is not. Okay, the answer really is not. It all starts from this, which I'm sure everyone in this audience recognizes. This is Maxwell's equations, and you have there D, the displacement field, which basically describes what the sum electric field will be inside a material, yeah, because of an exterior field, the E field, which is from the vacuum. Now, in terms of industry, that could be a signal being transmitted. It could be a signal you need to push through a wall or push through a person. And what this describes to you is how material is going to change that. Quite simply, what's going to happen? We're going to get, oops, a bit faster than expected. We're going to get this happening. The effect of this E field on that material will be to cause polarization inside. Now the question is polarization of what? Material is made molecules which are made of atoms which are made of charges. And at the most fundamental level, the entire world that we look on is one of electric charge. We have the nucleus, positive. We have the electrons around it, negative. And as far as we're concerned, that's all there is. Positive charge, negative charge. So the moment you put a field across material, the collections of charges, which we will loosely call atoms, sometimes call them molecules, will feel opposing forces. Opposing forces will lead to motion of some form, or at least the attempt at motion. That is the polarization. The action of the external field on the materials that we use and see today is one to orientate or to deform that electric structure that in reality that's what they're made of. Now, this deformation we can describe in terms of dipole moments. So this polarization vector I've written here is really the sum of all the microscopic dipole moments that you have inside there. At a lower level, a dipole moment is nothing except the charge multiplied by its position, and I'm summing over all the charges in there, everything, all of it, not leaving a single thing out. Now, how this actually sums up is not simple. At the end of the day, yeah, we're in a thermodynamic state. These materials, they have to react to their environment. They have to react to each other. And in fact, we can relate that reaction not by just a simple summation. It is not a simple summation, but a thermal averaging with the surroundings it has around it, but eventually reduce it to not much more than some reaction to that external field. Now I'm going to stay in the linear regime. Excuse me. I'm going to stay in a linear regime and not talk about nonlinear effects. Okay? Just simple reactions. That's what we have. That, Ishai, we call the susceptibility. And what it does, it describes for us how a material will change the nature of the field on it. And it will be responsible for telling you how this is going to relate to this. Now, most materials are isotropic. And so this displacement vector, displacement field rather, will point the same direction as the original E field, but not always. There are materials where that will not happen, specifically in crystals. But for now, we're not going to talk about those sort of materials. We're keeping things simple. So, what this really means for you, you've got problems to put signals through things. Things get bounced around. Things get absorbed. What this means for me is I have an amazing window into those materials. And by understanding what's going on in these two simple equations, I can grasp an idea of how these materials are made, how the constituents will act to each other, and why, and what will happen should I then go and change somehow those very conditions of that material, either by applying pressure, or temperature, or changing composition, or changing pH. And by this, I can attempt to divine what the nature of that material is and what I can do with it afterwards. And this comes us all the way back to industry, because then I can design materials. Then I can try and understand how to exploit materials. Okay, so that's why it's a facetious question, but the answer is far more fundamental. So what's this going to look like? Okay, now everything that I'm looking at is contained in this, and in fact contained in that original equation, D equals epsilon, the dielectric permittivity, dot E, the external field. So what does epsilon look like? Because that's what it really comes down to. That's what I look at, that's what I need, that's my bread and butter. Well, this is taken from Wikipedia. You can find it almost anywhere. And it's actually not a bad description of what we see. Now you can see the scale here. Yeah? It starts at kilohertz. Well, actually for me that scale starts a lot lower, even down 10 minus 6 hertz, 10 minus 2 hertz. And it's going all the way up here to UV. Okay? And of course it's a logarithmic scale. Now you can see there's various different types of behavior here. Up until about here, 10 to the 10 hertz or 10 gigahertz or 100 gigahertz, everything is looking like this. Now, this permittivity is a complex coefficient. It has a real part and an imaginary part, because it's also related to energy losses inside. So the real part will look like this. Here we go. And as I get past the 100 gigahertz range, I begin to see oscillations. And I can start to relate different types of molecular motion and atomic motion to these pictures. Beyond here, terahertz and above, I'm really looking on the level of the bond between atoms, stretching, IR. Okay? Higher, visible range, electronic. I'm exciting electrons, deforming them, moving them out of their orbits to higher orbits around atoms. There's a wealth of spectroscopies up here. My bread and butter, however, is down here. Here is where we actually have motion, orientational polarizations. We cause molecules to rotate, to move, to shift. We cause ions to move. And it gives us spectra which look like this. So let's talk a little bit about what we mean. In the higher region, we'll start with that, deformation polarization. Quite simply, I stick a field on there. The nucleus, which is for hydrogen 1,800 times heavier than the electron that goes around it, will barely shift, but the electron will, and I get a deformation. Okay, this is a classical description. Quantum, I move it to a higher energy level and then it simply comes down, and as it comes down it simply puts out a photon, and we can see that as light. Go down to where I would like to be. Now if I've got molecules and I come down in my frequency range, I now no longer excite them. I'm actually much more classical. By putting a field across here, specifically if that field is oscillating at a specific frequency, that molecule, here we're using water as a good example, will try and follow the field. There'll be a torque, and so it will try and revolve. Orientational polarizations. Now, it won't do it simply, because it's surrounded by a whole bunch of other molecules. So we'll have to interact with that environment. And how it's going to actually reorientate, that's going to depend on the environment. If I have, coming down for even lower frequencies, something like an ionic liquid, ions floating around, stick a field on them, positive goes one way, negative goes the other way. And I get a separation. If I do it slow enough, I'll get a conductivity. So all of these are the possibilities that we can have, for motion inside material. Orientation, however you want to put it. All of this we can then investigate. If you have any questions, by the way, don't wait till the end, because you will have forgotten the question. Quite likely I will have forgotten the answer. So please, if there's something in the way we're going, just simply raise your hand, ask the question. Now, consider this much more as a discussion rather than a lecture. Okay, so just feel free to answer anytime you want to. So how are we going to measure this? Well, whenever we have something which is low frequencies, long wavelengths, we can consider sample cells that allow us to measure relatively easy. And the easiest way, of course, is straight from, first year electricity, capacitor. So, if I take two plates, stick a material between them, the dielectric permittivity of that material will affect, of course, the impedance that I could then measure off them. I can simply put an impedance meter around them, measure the impedance. And I can relate that impedance, to the permittivity of that material. Now for me, that will be a complex number. Why? Because we know that that impedance will have a change of phase, change of amplitude. Simplest way to measure that impedance, you just measure the current that you get off, voltage that you put inside. And to talk about what that change of phase will be and that change of amplitude, I need complex numbers. So it's a complex quantity. Of course, it would change according to frequency. Now you'll see here the electric field that I've drawn inside looks parallel. This means I'm talking about using frequencies or wavelengths which are much, much bigger than the size of the plate that I'm looking at. Put it practically, megahertz and below, tens of megahertz, even gigahertz and below, depending on what I'm looking at. Now, the capacitor can have many different forms, and I've put 4 of them down here, quite simple ones, from the straightforward capacitance, and next to it is a normalization factor, the geometric capacitance, which is basically the capacitance that it would have if it was just simply empty, just air inside. So epsilon 0 there is the permittivity of free space, 8.85 10 to the minus 12 farads per meter. But it could also be a cylindrical capacitance like we've got here. Now, I've actually drawn on this one field lines which are coming out the top. Yeah, because if I go to the right frequencies, higher frequencies, this will start to act like an antenna and will actually transmit outside. Then the wavelengths that we're talking about are beginning to be on par with the sizes of the sample cell itself. But for the moment, we'll pretend that everything's good and that it can still be considered as a straightforward capacitance. And the C0 of that, its geometric capacitance, will be given by this. Okay, where B is the radius of the outer electrode, which is this one here, and A is the radius of the inner electrode that you have there. The field will be radial. I could use a microstrip, a little more complex. The way the microstrip is made will, to a great extent, define what that normalization factor will be. And in fact, to actually get it, you just simply measure something that you knew and then relate one to the other. Or I could use an open-ended coaxial probe. As you know, the only people in this country who have an open-ended coaxial probe that can be rented are in this room, which is good to know when you need one. Well, I leave that to Owen to decide. Yeah. Or 2 pi? Or 2 pi, yes. Yeah. Yes. So yeah, but once again, what we've got here, the field lines are coming from the inner electrode, which is usually the signal carrying part, and the outer electrode will be the ground. And what you've got here, you can see basically it's a fringing capacitance between the two in the immediate vicinity of the opening itself. Now, that can actually get you to quite high frequencies, which is why it's actually a very useful way to measure. And we'll talk a little bit about probes as we go along. You can calculate it. It's C0. It can be done, and that's what it will be. Although more normally, you'd simply find a known material and try and simply quantify how much it would be. All this material that I've got here, basically, you can turn into an electrical picture which looks something like this, not very much more. Now, this would be your impedance of your line that's connecting it all. Because as you know, I don't have to explain, it's one of the joys of lecturing to such an audience as this. I don't have to tell you about the vagaries of impedance analyzers and VNAs, about their reference plane, where do you measure, exactly how you measure, what happens with the line, and you all know that stuff, which is great. So you've got the impedance of the line over there. You've got the impedance of your sample here. Here expressed as a straightforward pure capacitance and resistive element. And you've got a little bit of fringing capacitances as well, which you want to take care of. Now, that's what you're seeing here, these fringing capacitances. Okay? Now, a fringing capacitance can look like just simply another capacitor. So, if you've got basic electrical circuit theory in your mind, very easy to do this sort of research. You could ask, why hasn't it been done more in Israel today? And that's an extremely good question. I wish I had an extremely good answer. Now, all of this has been taken from this excellent book, and I highly recommend people to buy it and read it, and not just because I'm one of the authors inside. There are a number of Bibles, and we call them Bibles, for dielectric spectroscopy, which you can buy, which will always be a reference. When it comes to biological samples, this is the Bible to go looking at. You may notice that Yuri Feldman is also sitting in the audience. So, let's talk the other part, calibration, an important thing to do. How do you actually calibrate? Well, this is taken directly from the Keysight manual for impedance analyzers. One of the great things about Keysight is that they do have an awful lot of basic material out there available for people to read. Many people don't bother, but they're great books. Really good technical notes. So if you have something like this would be connected to an impedance analyzer. It's also good for VNAs as well, up to a certain limit. You could describe the circuit, which would be basically your line coming out of your analyzer to your sample thus. So you've got your material, which you are checking. You've got stray capacitances here, which are related to the sample cell you use, the connectors you've got, to the wires themselves. You may have twists inside the wires, so you're going to have some form of RL, some inductance that you have to consider too. And you would like to get rid of all of these if you want to see what the real impedance was over here. Now, if you're like me, and you're in a very poor university, and you can never buy what you'd love to buy, and you have to use old equipment from the 1990s, like lock-in amplifiers, which are almost digital, almost, because most of them are analog still. This is your bread and butter to be able to make a system that will actually measure something. If I have one big complaint in academia today, it's that I'm getting students who have absolutely no idea what that is and could not build a simple circuit or could not build a simple analyzer, which is very disheartening, because while I'd like to blame someone else, it means me, as academia, have failed. It also means, and that's a bit of an aside now, that I'm also not serving you. Because if the students are coming out of my laboratories not being able to do that, it means they're going into your workplaces not being able to do that, which is a problem, I will admit. Yeah, but so, let's say anyway we have a student who can do this and can understand the idea of the calibration. Well, to get these four terms is not so difficult. First of all, make an open line. So if you make an open line, basically the dominant feature will be those stray capacitances. Measure your open line, whatever impedance you've got will basically be due to them. Then close, make a short at the end. You will have shorted out the stray capacitances, and then the dominant term will be whatever inductances are still in that line. And therefore, whatever impedance you've got is coming from these two. Combine them all, and you will get a reasonably easy algorithm to get the right measurement. You can go one stage further to account for what these can't account for and use a simple four-matrix system, an S matrix, and now you'll measure your open, you'll measure your closed, and a very well-known load. And then once again, you can get what you need to see. So in some ways, this is really simple science to do, or at least it should be simple science to do. So here's some examples. If you've got the money, you invest in one of these little beauties. Nova Control BDS 80 dielectric spectrometer with integrated temperature control on flow nitrogen. It means your sample stays at atmospheric pressure, which is always useful. Capable of measuring the dielectric permittivity down to an accuracy of tan delta 10-4. Extremely accurate. Amazing machine. And it can do that from liquid nitrogen temperatures, minus 90 degrees K, all the way up to 400 degrees centigrade. Massive temperature range. And nowadays you can get this with special pressure units as well. So you can now measure your samples under gigapascal pressures and see what that does to them. You can get it with high electric field that you can apply. So you can apply over samples which may be only a millimeter thick, a 400 volt field. You can really stress your materials. And if you really want, you can then look at a four electrode system for this as well, and then you can start doing some electrochemistry with it too. So it's a very versatile machine. Excellent results. They are the world leaders today. They basically have dominated the market. The only problem, of course, is the cost for that machine. About €250,000. Or you can come down, if you want to go to higher frequencies, you can come to the area where I know you're going to feel much more comfortable. Vector network analyzers. And here's a picture from my lab. We've got here, this is the new FieldFox. FieldFox is nice. Has a dB range of about 110 dB, which is very good. It's not as good as the standalones on the table, but it is portable, which is sort of nice. You can do all sorts of things. It has a few nice features inside. Now, I've set up here, in this particular picture, this is an S11 measurement where we've terminated the sample, the line, with a simple sample cell. These sample cells were developed by Yuri Feldman all the way back in the 90s. So that's a cylindrical cell with a very small electrode there inside. This diameter is about 3.6 millimeters. The inner electrode is about 2 millimeter diameter. The electrode length is only about 1 millimeter, 1.5 millimeters. Now, it's a small volume, microscopic volume in fact, but with that you can measure water, you can measure blood, you can measure all sorts of very interesting things, liquids of all forms. So you can see here, this has been calibrated. This is a 2.4 cable with a connector here which is taking it down to an SMA, which means I'm limiting myself up to about 18 gigahertz in this particular case. And it's been calibrated up to the end of this sample cell. And then we're further calibrating by making a short circuit measurement on that sample cell and an open measurement on that sample cell. And from there, trying to get what we get. Okay? Now, how are we going to get it? Very simple. Simple relationship between S11 and the impedances at the end of that line. So we're looking basically at an impedance mismatch. And we're measuring from the impedance mismatch. Okay, now once again, the impedance of our sample is quite simply the impedance of a capacitor. So it's very simple. There are limitations on how far you can go with that. You are going to get multiple reflections inside this cell, and you can actually see here on the screen that we have multiple reflections starting as we creeped up beyond about 5 gig, I think there. Okay, so yes, you are going to get multiple reflections, and you can then make an adjustment to this to account for those multiple reflections. It becomes a little bit more complex. The maths is more complex, but we have MATLAB.
But you can use a VNA that has this feature. You can look at the kind of time slot and measure only in this time slot, so you know when it's the right reflection.
You can, but then I lose information. Remember, my purpose in all this is to understand the material I'm going to put inside there, how it changes all the way up. So if I do something like that, I will see that very narrow stuff, but I'm losing information outside the window on the other side. Okay? So I much rather prefer to accept there's a multiple reflection and then algorithmically work it out and then simply remove it from there. Now, there are other methods to do this. There's a time domain method to do this. In fact, I grew up on time domain methods to do this using an oscilloscope, which actually has a lot of advantages. In many ways, it's actually a lot more advantageous than using a frequency domain. Not the same sensitivity, mind you. That is a problem, but still. But anyway, this can work quite well. Works not bad at all. You can go on, and you can use the open-ended coaxial probe. This is a picture from Yuri Feldman's laboratory. And there you can see the probe that's being used. This is I almost said adjuvant. When I first started out in science, it was called HP. And now it's Keysight. That is the Keysight high performance probe. Now, when we first started using these probes, we were very intrigued to understand how they were getting the answers they got. So we went and we dug back and we went through the libraries. And eventually, from 1951, we came across a very heavy theoretical paper which explained how the admittance at the end of a probe terminated onto a semi-infinite plane would work as an antenna. The bottom line from all of this was that you would get a series expansion of the admittance at the end of the line, which would depend upon the dielectric permittivity of the material you were touching, and it would expand out like this. Now those coefficients, C1, C2, C3, they have a slight dependence on frequency, so you have to calibrate. We then went forward a few years to see who had actually quoted this particular paper, and we came across, I think it was in 1975, another paper where we actually saw the first ever probe design of Agilent. So we know where it all came from. So that's basically how the Agilent software works. Now, today, you don't bother with this. You simply get the package as it is. It comes along with a nice software package which you load into your VNA, and it gives you directly up to 50 gigahertz the dielectric permittivity of whatever is at the end of that probe. That opens an awful lot of research, and much easier research, I have to admit. So this is now a very useful option that we have, and in fact, I have to be honest, somewhat better than using the cylindrical sample cell, because I can get all the way up to the 50 gigahertz level. Another way is this, open space. You can do open space measurements. Now this is taken almost from optics. So that's what you've got here. You've got the VNA, you've got the horn antenna to transmit your signal, focusing mirrors to focus it to a spot size onto your sample. It goes through your sample or is reflected back depending on what you're measuring. And then the signal is collated by another couple of focusing mirrors and focused inside your horn antenna. There is a problem doing this. If you want to have something like I've got on my table here to do that, you should be working at 25 gigahertz and above, because the spot size that I can focus here is basically it's geometric optics, and it means it's at least twice the wavelength, which means for 25 and above it's about that big. If you would like to look at something in megahertz, the spot size, it doesn't even bear thinking. It doesn't even bear talking about. If you would like to see what a mirror looks like for gigahertz, it's actually bigger than me, and it weighs a ton. But if you are still interested at looking at high frequencies, and let's face it, today we are. Okay, today we most definitely are, because we have electric cars, we have 5G. The shielding market is now becoming something very, very important, and everyone needs these details. You'll be very surprised to know there is no lab in Israel today capable of measuring this. Hasn't been set up. The standards that industry is requiring of these materials were last updated in 1996 for measuring them. It's quite ridiculous, but it's true. So you can do this too. And there you can see the same field focus. You can see I've got a signal here. The material which you can barely see there is a plastic which has been doped with carbon nanotubes, making it an extremely good absorber.
What about lens behavior? Can open your focus on
The lens behavior can. You have to be very careful. You have to use the right sort of lens. Now, there's a problem. I mean, you can make lenses. You can make them from Teflon. You can make them from many plastic materials.
this particle, this small piece of plastic that you're
Yeah.
should also impact your.
Oh, it does. It can. It depends exactly what you've got. Now, if you've been careful to make sure that it is parallel to it, then it's thin enough. Then mostly what you're going to get is simple transmittance through and absorption there, a degradation of the signal. And you're not going to get much dispersion or scattering, which is going to affect your final signal. Yeah? There is a whole market out there for radar materials. Now, for radar materials, these things, they work specifically by dispersing your signal. And they have to be thin, they have to be pliable. And the idea about these, radar camouflage materials, I forgot the additional word, which is rather important. Now there you actually want to measure that scattering. So, Keysight actually has a very nice solution for that. They have a proper ellipsometer where you can measure the scattering coming off as you come in at different angles. But for most of what we want to do, yeah, this is good enough, and the scattering you will get from the material itself, if you keep it thin enough, is not going to be relevant. And in fact, your S11 is going to look something like this, and that will be the transmittance through the material itself, which will be, first of all, the Fresnel coefficients as you hit the front face of it, the absorption as you go through it, the Fresnel coefficients as you come out the back face of it. And if you really want to do the work, and you can actually get all the material characteristics that you want from this measurement. Yes?
Just going back to the coaxial probe method for a second, what's the advantage of using a VNA architecture versus an auto-balancing bridge?
Basically, well, it's a good question. I hate good questions. VNA is there. It's much faster. Okay? The days of the auto-balancing bridges are well past us. The VNA simply can do all that that could do, and it can do it faster, and it can detect much better.
In terms of range of impedance that you're able to measure?
Well, yeah, I mean, you could argue that. However, good VNAs today, 120 dB dynamic range. I'm not so sure that we'd need more than that with a bridge. The bridges were highly important, yeah. When all this started way back in the 50s, when the first dielectric measurements are truly made and published, the bridge was the only way. But I think with the development of the electronics, the quality of what we can get now in terms of the VNAs, it's almost a moot question. If you're looking at the big four, yeah, Roden Schwarz, Keysight, and Ritsu, there's one other I forgot the name of. You're not going to help me? I get Ritsu, Roden Schwarz, Keysight, one more. Huh? Tetronics, thank you very much. They're producing excellent machines, great machines. There is now a Chinese manufacturer who's making a mini VNA, yeah, going up to 6 gigahertz with dB of about 90, costing about $600. So electronics have come to the point where the auto bridge is just, I don't think we'll ever need anything that to the accuracy where it could go, to be frank. So that's my answer. Okay, so I was here, yeah. So I forgot what I was saying. Yeah, so you can get all the material parameters out of this. Although for most of industry, specifically when we're looking at shielding, it's just simply enough to know the absorption that we're going to get per thickness of the material you're using. So these materials are based on PP, PA, yeah. That is the open line. That is just the pure plastic. I'm not going to tell you which is the company that gave this to me. But you can see as they increase the amount of carbon nanotubes inside, you can get easily the sort of absorptions that are required nowadays for electronic shielding in electric cars, okay, or in 5G applications. Okay, 40 dB. So that's a big thing that's going to come along. That's something which I think the industry is going to push out there towards academia more and more. So there's plenty of ways to measure. The real question then comes, what do we actually get from all this measurement? So let's talk a bit about the functions that we use to model the materials that we measure. So this one, the Debye function, first brought out there by Peter Debye, 20s, in the 20s. This particular modeling is useful because that can be derived from the first principles. You can imagine a polarization, you can imagine it changing according to time, and eventually you will get to this equation. Let's look at what's inside it. You've got high frequency components, basically the residuals of whatever's outside your measurement window, which are going to give you this tail. You've got a dielectric strength, which is the difference between the high frequency residuals and your solid, your steady state solution. You've got a particular characteristic frequency, okay, which represents, yeah, the optimal position for absorbing energy by that material. Which field will it take best of all? Okay, and this is all summed up in this particular behavior, which is really a Lorentzian in its form. So that's the Cole. That's the the Debye function. Now, 1941, Kenneth and Bob Cole came out with another function because they noticed an awful lot of materials that they were measuring just didn't obey this. And they came out with a phenomenological equation called the Cole function, which is this one. And the difference is what they saw was that if this black line and this green line, that's the imaginary component, that's the real component, would show to you what a good Debye material would be doing, many of their materials deviated. The peak broadened out, yeah, and was flattened down. By trial and error, they came across this equation here, which could fit that by the addition of an exponent here. The exponent alpha goes from 0 to 1, and if it's 1, you have a debye, and as it gets lower towards 0, your peak will flatten and distribute out more and more. Initially, this was just purely a phenomenological explanation of what they're seeing. We now have an explanation for what that actually means, and I'll talk a little bit about that explanation. By the way, if it gets a bit heavy and we want to have a break, just tell me, because I can talk forever. Okay? There are other ones. There's a Cole-Davidson which came out afterwards in the 1950s, which accounted for the fact there seemed to be asymmetry in some of these spectra. There was a shift towards the higher frequencies, and these peaks would change. But I'm not going to talk about these two, although they are very common. I'm going to try and keep all our conversation only on this one. I think it's enough for one lecture. So, putting these ones aside, let's just simply talk about this, the Cole-Cole function, and what it does. Well, it depends what you're measuring. You will have noticed until now I've barely talked about what I measure. So, you can see some strange things happening depending on what you measure. This is, by the way, taken from a review article that myself and Yuri Feldman wrote, which I forgot to put up here, the citation. So, if I'm measuring water, and here I've made a schematic of what water looks like, and if I look into the molecular dynamics of water, it's just not molecules twisting around like this. They actually interact with each other, and they act like a cluster. And what I actually see is an apparent dipole moment which shifts. But if I then start putting stuff into water, the behavior changes from that nice, easy to buy picture that I showed you. What happens is we see that as we put stuff in, the dielectric strength, this difference between here and here, goes down. We see that depending whether it was an ionic substance I put inside a solvent like salt, I'll see that the relaxation time, this characteristic frequency, will shift to higher frequencies as though things are getting faster. I'll see that there'll be a broadening as well. But if I put something else inside there, like a dipolar material, like glucose, something which isn't an ion, what I see is something a little bit different. I still see degradation of the dielectric strength. It still goes down, yeah. But everything gets slower. The relaxation times shift to lower, to slower times, higher, lower frequencies. And once again, I see the broadening. So this is the beginning. Somehow, the nature of what water does changes when I stick stuff in. It's not like I've just got a molecule like inside there of glucose, or an ion from salt inside there, and there's just water around doing its own thing. No, they interact. And what I see in my frequency there is the result of that interaction. And that's what I have to pick apart. That's what I have to try and understand. So, first thing that I can talk about when I look at ions is that water gets around them, sticks to them a little bit. Not too much, just a little bit. Well, the first thing that does is mean there's not so much water left to participate in this collective water motions. Changes what I see. With things like this, it's even worse, because not only is there no water now participating in this, with molecules like glucose, where there's a possibility to do H bonding, they join. They make bigger clusters. Things become slower. So clearly these interactions affect the spectrum that I can see. Let's continue on. I'm sure if there's stragglers outside, they'll drift in as time goes by. So we got to this slide, and we started to talk not so much about how we measure, but rather what we measure and what we can discover from what we measure. So let's take the simplest of all, salts and ionic liquids. We'll concentrate only on salts. So, salts have been measured an awful long time. In fact, you can see this slide here. This is from a paper from 1987 by a German researcher, Udo Katze, one of the, if you like, the pioneers of dielectric spectroscopy and certainly of looking at salts. So here you've got two examples. Simple ionic solution. This is just pure salt, table salt at various concentrations. And as you can see, this is what you'd expect with water, this one here. And as you add, it simply goes down, decreases, shifts to lower frequencies. This is all at, I think, 37 degrees centigrade. It's all the same temperature. Okay? And you can see very slightly there's a shift in the frequency. The more salt you put in, the higher frequencies it goes. And when you start analyzing this, you get to these sort of ideas. Okay, you dumped a load of salt inside the water. Salts are basically held together by ionic charge, yeah? It's basically Coulombic interactions. You've got a charge, you've got a charge, you've got the Coulombic field. They're held together by mutual attraction. So you put them in water. Water's a dipole, and it begins to break apart those attractions, and basically water seems to surround them and drag them off, and they simply dissolve inside. So this gives you a sort of idea. There's hydration shells now to be considered. So we've got hydration shells. That sort of accounts in some ways why we start to get this degradation, because beforehand, pure water, as I said to you, it's not like you've just got water molecules, each one individually doing whatever it wants to do. No, no, no. They are bound to each other. They are bound by something called an H bond. An H bond is a mutual attraction which is not strong enough to be a chemical bond. It's not permanent. Yeah? But it's not weak enough to be considered like just a simple electrostatic interaction. It's there and it holds them for a certain amount of time. Now, what that does to water, it means that water, when it dielectrically relaxes, does it in a cooperative fashion, as a group, a cluster. Okay? And that accounts for why we see the peak of water. But when I put something inside, and when I put the salt inside, some of that water is attracted and kept around the salt in the form of a hydration shell. Others are simply disturbed by the presence of the ions inside there. And in fact, you could almost say there's less of that cooperative type of motion. And so we see shifts and we see changes in that spectrum. So how can we explain that? Well, what I want to do is explain why does it broaden out. So I'm giving you this really simple model to look at. Okay? Now I've got a grid, and I've put positive charges on my grid, and I'm fixed them to the grid. All right? And then I've thrown in a negative ion of some form. Now, if you remember at the very beginning, we talked about that polarization vector as the sum of charge multiplied by the distance where the position is. So I can actually make that polarization vector. You can't see it very well because of a very poor choice of colors of mine, but there's actually a vector there. And it is the summation of the charge times the position of all of these ions together. Now, if somehow I cause this one to move, I'll change that direction. I'll simply change it. Now remember, what is the polarization vector? What causes it? It's the fact that I put an electric field from outside. That's what causes it. Okay? Now once again, I've decided that the positive charge can't move, and only the negative charge, because it's my material. I'll do what I want with my material. So, simple motion causes that to change. Well, first guy to really consider simple motion, yeah? Brownian motion if you want. Einstein with self-diffusion if you want. Says, look, if you take your particle moving and you say you can just move one step each time, same size step each time, but you've got to do it all the time, you get to something called self-diffusion. And that's the mathematical equation which relates the change of your position in time to the change of your position in space. Okay, and if you do that, it will move around like this. And you know what? That will change my vector, change all this addition up here. And with a little bit of maths, I'll get a Debye equation. And that's what I'll get. That's what I see in water. But what if I remove that really stringent condition and I say now you don't have to move the same size step each time. In fact, you don't even have to move. You can wait. And sometimes you can make a bigger step. And my motion begins to look like this. And finally, the last one. Still going to get change of that vector. But I can't describe it the same way now. Now I have to describe it something much more complex. I have to use something called anomalous diffusion. Now, that's a lovely set of numbers. And it's really horrible when you look at the maths. But let me try and pick apart what it's telling us. It's saying, look, this function, which could be the function of position, it's going to depend on where you're sitting inside this area, where all the ions are. And the way it's going to have that motion and it's going to change in time is not going to be so simple. You're not going to be jumping each time, and you're going to use something called a fractal derivative to actually do this mathematically. But it says quite simply, if I take apart all that stuff, all those numbers, it simply says, you're going to wait, you're going to move fast, you're going to move slow. Continuous random walker. And if you do it at your maths, that will give you that, the Cole equation. Now, all of that change in how you can move through your system in terms of time and in terms of space is ensconced in that little parameter, alpha. It contains it all. Now, how Cole came across this equation phenomenologically, is just a pure piece of luck. How this was first described was by a guy called Raymond about 100 years before. They were never linked. It took a guy in Yuri's lab, Ryabov, who came from another quite big laboratory in Kazan, who actually linked them for us and told us basically what this thing is telling. So what is it telling? Well, what it's saying is the following. In reality, in real life, nothing is ever simple and straightforward. Motions are always going to be continuous, slow, they're going to wait. So all of diffusion just simply the change of direction, the change of position, is going to be anomalous. So that's the right equation that's going to tell it. That's one side. Two, not every time you decide to measure, to ping, to check, will something happen. We're going to get distributions of times. Three, this is going to give you some unusual motions, things called Levy flights. A particle appearing here, disappearing and suddenly appearing over here. Unusual behavior. Well, in my world, we don't see the space part. We simply measure in time or in frequency. So we'll scrub that out. That will be averaged out. And my Malus diffusion will look like this now. So I'll see all of that space information over there is now ensconced in this alpha, and it appears over here. So those will be related. Now, as a physicist, I'm always talking about energies, energy barriers, things to move if I've got to overcome those energy barriers. And in fact, I can translate this idea of continuous random walkers, of motions, of waiting times, into an energy landscape, which can be very, very varied and have many different scales. All of that comes into this, which gives me the Cole. Now, I can also look another way. I can talk about a memory. I can say my particle can't move to here if it wasn't here at the very beginning. So the very act of moving here precludes the knowledge. Well, knowledge isn't the right word because knowledge includes consciousness, but you get the idea, yeah? Precludes the fact that there was a trail behind it. Causality. Well, one way you can explain causality, one way you can use causality is something called a memory function. This is what this little equation does. But if I can, well, this is the memory function. But if I take this idea of this landscape and think that it has many, many different scales, from the macroscopic of my entire sample all the way down to the microscopic of the single dipole itself, I can begin to believe that there's going to be scaling involved, which is this idea of fractal. Take all those things together and you get that. The simplest equation you could possibly imagine to explain that spectral broadening, which if you look at it, looks extremely boring. It's just a peak, which is a little bit broad. Yet inside here is some fundamental information about my systems. And this is that fundamental information. What that actually says, it says if you count each time your dipole moves, and if you do that in a specific time frame, a window, and then you take that time frame and you cut it in half and count again, and you do that process ad infinitum, or at least many, many times, you're going to find that the ratio of these two things, expressed logarithmically, is going to be maintained. It scales all the way down. It's like looking at a tree. You look at a tree, you see all the leaves. You go a bit closer and you look at one branch, and it still looks like the tree. You go even closer to a small little branch, and it still looks like the tree. You go all the way down to one leaf, and you look at that one leaf, and it still looks like a tree because it's got a sprout and it goes off like this. It scales all the way down. Translated, that means macroscopic phenomena in the dielectric world are purely and simply an expression of the microscopic relationship between our various materials. And it's all ensconced in this one little thing here. So if I can understand that, I can understand an awful lot. Here's some examples. This is salt solutions measured in Yuri Feldman's laboratory. And you can see here that's 1 molar, half a molar, 0.1 molar. This is almost getting to be water. Okay? And they broaden out, they strump down, and you can see we've got a strong conductivity as well. Yeah? But as you go down low and low, you come almost to water, that conductivity will go away. Okay? Another example. Here, this is potassium chloride, this is sodium chloride. Different ions. Well, in general, they look the same. They still broaden out the more I put in. But there's subtle differences inside there. Subtle differences. Let's look at them. Now they're on the same. So I've got here on this particular graph, just taking data from here and data from here. I've got the sodium chloride, that's the black and the red, these two, at 0.1 molar and 1 molar. Here's the blue, there we are, sorry, I've got it wrong. 0.1 molar is the black of sodium chloride, and the blue at 1 molar of sodium chloride. They look pretty different. Yeah?
Does chirality have any effect?
Oh, yes. It does, but not in these ones. There's no chirality involved here. Right. But yes, chirality can have a massive effect on your signal if you know what you're looking for. And if you're looking for something in chirality and you can actually put circular polarization into a sample, yeah, you will see these effects. I didn't put anything in this particular one, but the classic one that we all know about is looking at the reflection coefficient from the human hand, which is affected by the sweat ducts. They are very chiral. They're all right-handed. Well, 90% are right-handed. And believe me, we can see the chirality in a reflected signal. And we've done it. But for this, no chirality involved. But now, the red is 1 molar of potassium chloride, and the green is 0.1 molar. Or did I get the wrong way around? No, sorry, the other way around. That's 0.1, the red, green is the 1 molar. They're different. Electrically speaking, they're the same. A potassium ion has a charge of +1, a sodium ion has a charge of +1, chlorine is the same in both of them. But they don't behave the same. They change the signal I see. And here's part of the reason why. Basically, you can see in terms of the sizes, they are very different. They are extremely different. Here's a sodium. That black dot is the size of the ion itself. It's at a certain size. It means there's a certain electric field close to its surface, which means it can hold a certain amount of water for a reasonably long time, about 20, 30 picoseconds in its immediate vicinity. Like it's grabbing. Yeah? Like a big guy running through a crowd and just grabbing people along with him. Potassium, however, is bigger. So strangely, although he has the same charge, at his ionic radius, the field is weaker. Can't do anything. It can annoy water. It can certainly disturb water around it, but it won't hold water on it. No. Chlorine is even bigger. Now, if I was to show you the electronic configuration of these ions, you'd immediately realize what we're talking about. Because as you go up in the electronic scales, yeah, that's small, that's big, that's on 2 shell. This is all 3 shell, 4 shell. They just get bigger and bigger. Although electronically they look the same. Chlorine, massive. It will disturb water around it, it will perturb water around it, but it won't hold water. That's why they give us very different signals. This is also from Ude Katze, and also to be in a paper that we are publishing very, very soon, from the work of Cindy Gore, what's her second name?
Cindy Galindo.
Galindo, yeah. This is called the chaotropic scale. Basically what you've got here on this scale, this is what's called the residency time. It shows you how long an ion can hold a water molecule in its immediate vicinity. Okay? And it's normalized on water itself. Okay? Now, sodium is called positive hydration because it can hold a water molecule around it for about 20 picoseconds before the water molecule will break free. Where's magnesium? Lithium's even more. I don't have magnesium on this scale because it won't fit on this scale. Magnesium can hold a water molecule around it for about 1 microsecond, which means on this scale it is somewhere at the same height as the jets that land in Ben Gurion when they come over. Okay? Potassium, no. Chlorine, no. They will disturb water around them. They will simply throw it out. And we see this reflected in the spectrums that we can measure. So let's have a quick look. Now I told you there was conductivity. So here's the conductivity. Yeah, conductivity for sodium, conductivity for potassium. Now, the unusual thing here, well, conductivity in general, you can relate it by what's called the, where is it? Oh, sorry, didn't have it there. Sorry, we'll talk about this side. So, we took that expression for alpha and tau, we changed it around. N is now represents the interchange. the ability of water to move in to that vicinity and to move out. How many times is it actually going to happen, if it's going to happen at all? Okay? And we now use the alpha as that scaling parameter, as that power law, relating it to that relaxation time. And it has a cutoff. A minimum, actually no, a maximum time. And all of our relaxation times at each particular temperature that we measured up here, this is the temperature changes, yeah? All of them are faster than that cutoff time. What does it mean? Well, we have explanations what it means. It actually reflects the scaling that we have inside there. The multiple levels of different energy barriers which must be overcome between water to water when you put the salts inside. Basically, it reflects all of this. It reflects water moving in, moving out, or being disturbed by the bigger ions. And how, if you change these concentrations, you will affect that seriously. And in fact, the amount of concentration that you'll get will give you various scales of motion you can have and behaviors that you can have, and it all is ensconced in this equation. So let's look at the DC conductivity. Well, that is called the Nernst-Einstein equation, and what it tells you is that your DC conductivity will depend upon the diffusion of ions, the strength of the ions, and the concentration of ions. And that is something known in hydrodynamics, fluid dynamics. It's old as old can be. But it doesn't work here. It doesn't work here because this is not self-diffusion, as we already talked about. It's anomalous diffusion. And so you have to make it fractal. So you have to put in here an exponent. That exponent reflects, if you like, the motion of ions to come to the electric phase interface, because it's DC conductivity, and actually get through a double layer of ions accumulated at that face and come through the other side. So, more information. All this from one measurement. Well, let's go to something else, a little bit more practical. Once again, this is research that I was involved in the laboratory of Yuri Feldman, and it's the aging of red blood cells. These are red blood cells. These are good red blood cells, which will keep you alive. These are bad red blood cells, which will kill you. The difference between these two is that they were basically taken from blood banks. This is the fresh one. This is what it will look after about 42 days in a fridge. Because blood cells live. They continue on. And eventually, they simply die. Now, why is this so bad? Because that shape, that concave shape, means they're very pliable. They can get into the capillaries. They can get and deliver oxygen to wherever it's needed. They can remove carbon dioxide from wherever it's needed. Once they go like this, their skeletons are basically rigid. And if someone got that blood, it would be quite likely to kill them. So what do we do in our blood banks today? Well, after 2 weeks, we start chucking stuff away. Because you can't really tell. You don't measure it, they don't check it. It's impossible to check and measure. Well, not quite impossible. You can do it. And this is a series of experiments we did. First of all, we're measuring here with the probe, the coaxial probe, blood at various stages in its life.
You are interfering with the blood with some metal explode, right?
Yes, this definitely. However, you can design a microwave probe which should shoot through the plastic and sample the blood without interfering. And that was the idea here. But first of all, you've got to understand what happens with this. So here we're simply measuring the blood itself. So we're checking the blood. We're looking at the blood, we're seeing its dielectric signal. And that's what we're seeing. As things age, they change. Basically, they change. So here, dielectric spectra, 25 degrees centigrade, we're checking this. It's in, of course, a buffer solution, sagum. Yeah, purple squares, okay? And we have models which allow us to actually look at the cytoplasmic water, the water inside the blood cell itself. So that's the actual sample, and this is what we get when we remove the sagum and look at the water inside the sample itself. We can see this. Okay? Now, after a while, we see things begin to change in these signals. They change quite significantly. And in fact, when we do a fitting of those, and we start looking at different days that they've been in storage, you start to see this. Now, here you have the day. So 5th day after it was donated, 10th day, 15th day, all the way up to 50 days. We stopped at 45. That's what you do in a blood bank. No, we never kept longer than that. Blood dies after that much. And we're looking here at the relaxation time where that peak is sitting. And we see here, about 38 days, suddenly it drops.
Opposite pole. Red is tau.
Sorry, yeah, red is tau. My mistake. That was the elongation factor when you measure the actual blood cells themselves. But yeah, red goes up. Things become suddenly very rigid. When you look at the ability to be extended to the elongation factor of those cells, which is another physical measurement you can do, you see it drops at the same place. So basically, you see this. Now this opens a really great avenue. You could check blood in a blood bank. You could take a bag, you could measure it. Microwave sensor firing through, see what it gets. If it looks like this, problem, chuck it away. Rather than what they do now, which is after 21 days, they'll chuck it away anyway. Maybe great blood, but they'll chuck it away. Now, looking at this, we were able to find that other measurements have been made, particularly NMR, where they're looking at the spin lattice constants, and they'd noticed exactly the same behavior. That's that black line. So we had confirmation here. We have confirmation that what we're seeing is something real, that something is most definitely changing. And it is basically the fact that the spin lattice constant is reflecting what's happening to that skeleton itself. So when that becomes rigid, that changes. That changes the nature of water inside, yeah, which changes the signal we get, which is why they coincide one to the other very nicely. Anyone who's interested a bit more, you can actually read these papers. This is our paper. This was the NMR paper. So let's go another example of how we can exploit dielectric spectroscopy. Let's look at polymers. Okay, now this is quite low frequency. This is not the gigahertz. But it's there because it can explain a lot of what we see. You see we've got here alpha, beta, MWS, gamma. They're nomenclature for different processes that we can see in any measurement. The measurements we're making here were frequency scans against different temperatures. So what we got? Gamma, this very high frequency process. Yeah, that's basically local chain motions. Yeah, inside the chain segments, things revolving around each other. Beta, yeah, dipolar segments. You may have a particular dipole inside, and in fact we're going to see one on Viton. That can also revolve. That can also change. So we can see that do something. Alpha, the dynamics of the amorphous phase itself, the glass-forming nature of many, many polymers. How this is especially affected if they cross-link, and how that will change. And the Maxwell-Wagner-Sillars, this one, is interfaces between different compositions inside the polymer. Now, all of these are important to know about. They may affect the tensile strength of the polymer. They may affect how that polymer can be used in as a dielectric, as an insulator. They may affect the other properties of that polymer. They may change if that polymer is subjected to UV light and begins to degrade because it's been out in the sun too long. All of this can be investigated by looking at its dielectric permittivity. So I'm going to give you an example here. This is Viton elastomers. That's what Viton looks like. These are fluoroelastomers. They cross-link. It means they link up to each other. They're extremely hardy, which is why you'll find them in all sorts of temperature-dependent, heat-resistant applications, like O-rings and stuff like that. They're very, very hardy, partly because the fluorine that's involved inside there. But they have big dipole moments inside, and also side chain dipole moments. So there's the actual permanent dipole moment of the monomer of Viton. This is the one we're looking at, this one over here. But what's interesting to us is this, how that moves around. So if you do a high frequency measurement on that, now we're doing it in gigahertz, you can see there's a process, and that process is related to that revolution of that side chain. Now, we changed temperature on this one, and you can get from there an energy of activation, and there's the energy of activation that we can get. It's about 30.2 kilojoule per mole, which tells us something about how it's actually linking up, how much it's really is involved in cross-linking. So you can go a lot more deep into this, and you can get a lot more out of this. And I haven't actually shown too much of the higher frequencies we can do with plastics, but you can go a lot deeper. I basically have finished what I have to say, because I could go on material after material after material, but I think more or less I've given the message to the end of where that message can be. So I think it's time. Questions? Yeah.
How does the performance of these methods compare to more traditional analytical chemistry methods, like, I don't know, mass spectrometry and...
Each one is telling you something else, basically. The ones that you'd want to compare this to are more like rheology. Okay? So let's say, what do you want to do when you want to do analytical chemistry and you want to do some more traditional methods in that sense? You want to know tensile strengths. You want to know when a thing's going to fail. You want to be able to understand the action of UV light on a plastic.
Let's say analytical chemistry for the pharma industry.
Yeah.
For impurity.
So this will never tell you about the impurities, because it's not label. Yeah. So it's not like FTR where you can say I'm now looking at the the NH3 bond or something like that. It's not terahertz spectroscopy, which is a further branch of this where you're looking at maybe molecular wide vibrations on side the molecule. But it can give you information about how that particular defect may affect the material. Because basically, what do we see here? What do I see here when I shift temperatures here? Okay, I change a thermodynamic state. By changing a thermodynamic state, yeah, I begin to give enough thermal energy that this molecule can shift over an energy barrier back and forth, back and forth, back and forth. But what made the energy barrier in the first place? It could be the cross-link in terms of a polymer. But if you defect that polymer, that breaks down. And that number will change. And that may show to me, yeah, that this material will crumble earlier. Okay, so it will never tell me, like in analytical chemistry, you have this much concentration of this. But it will do what the analytical chemistry can't do. That will affect its behavior. Okay? So if you look at something like this is Viton, very fresh Viton, nice, just made, little disc, put in a dielectric spectrometer, measured. Take the disc. Hit it with a hammer repeatedly for a day. Take the disc, put it back inside the dielectric spectrometer. Do the same measurement. Visually, you can see nothing. It's a disc, you just hit it with a hammer. However, the repeated stressing of the material has had an effect. It may be on the level of actually interfering in terms of the cross-linking that you've had. It may be the formation of microfissures, which you can't even see. It may be aiding the penetration of water molecules inside there through microfissures. The dielectric measurement will show you that. You will see a change. Now, you could stress the material another way as well. You could do it by heating, repeated heating cycles. You could stress it by repeated bias measurements, yeah? Put an electric field over it. Strong electric field, on, off, on, off, on, off, on, off. You could cause the growth of microfissures of percolation trees. They will have an effect on the dielectric picture that you then see. So it will show you the behavior. It won't show you the analytics. Yeah?
Practical question. Can 3 we freeze the blood
Yeah.
in some way, hydrogen, or will it slow down the aging of the red blood cells?
Well, it may kill the blood cells by bursting them. They just explode. Why? Because the water inside, yeah, will freeze. Water is a wonderful thing with 64 different anomalies in its behavior. One of those anomalies is that when you freeze it, it increases its volume by 10%. Well, 4 to 10%, depending who you talk to. Okay? Instead of shrinking its volume as you would expect. What that does, it bursts the cells. Which is why, yeah, they tell you not to refreeze the meat from the supermarket. Same sort of reason. It's also because of bacteria, but it will do the same. Now, we know about this because we've also looked, there are certain animals which don't have this problem. They have particular proteins inside the blood which are antifreeze proteins. They cause water, when you cool it down slowly, not to crystallize and therefore expand, but to become glasses and to stay amorphous. Fishes are very famous. There's a particular frog, for instance, which you can freeze for up to 2 years and then defrost it and it's back to life like nothing happened. But in general, in the blood bank, you freeze that blood, it explodes. Dead blood, very fast. Other questions? Well, in which case, it only remains for me to thank my collaborators in all this wide research that I've been doing. That is Professor Feldman sitting in the audience, Anna Greenbaum, who I've done many a measurement with, the members of Yuri Feldman's team, the members of my team, who are hard at work. And thank you very much.